Example 5.1. What happens if a bar magnet is cut into two pieces, transfers to its length and along its length? Okay. When a magnet is cut transversely, that is perpendicular to its length, magnetic dipole moment, pole strength remains same and length of the magnet reduces to half. Suppose if you see the diagram, see this is a magnet now. We are cutting transverse, that is perpendicular. So it become two pieces. We are not disturbing the pole strength, and after cutting each and every side, that is north, and immediately on the either side of the cutting part, here it becomes south and here it becomes north. In other words, two short magnets were formed, right? So what about magnetic dipole moment? Magnetic dipole moment is pole strength into length. For each piece, pole strength remains same, length will be reduced to half. Therefore, magnetic dipole moment of each piece reduces to half of the original value. Now we'll see the second part. We are cutting the magnet along the axis. Suppose this is the magnet. We are cutting along the axis. When we are cutting along the axis, pole strength reduces to half, but length will remain same. So magnetic dipole moment is pole strength is m by 2 and length remains 2l. So again, magnetic dipole moment becomes m by 2. In other words, whether you cut the magnet transverse or lengthwise, magnetic dipole moment reduces to half of the original value. Okay. Now, we'll go for part B. A magnetized needle in a uniform magnetic field experiences a torque, but no net force. But an iron nail near a bar magnet, however, experiences a force of attraction in addition to a torque. Why? Okay. First thing is why a nail experiences force as well as torque, right? Okay. Now, magnetized needle. What is given? Magnetized needle. Already it is magnetized, means magnetized needle behaves like a magnetic dipole. We have already discussed when a magnetic dipole is kept under uniform magnetic field, it experiences by a torque because equal and opposite forces, net forces will become zero. There will be only torque 2 equal to mv sin theta we have derived. That is magnetized needle behaves like a dipole. Dipole is kept under uniform magnetic field. Okay, now we'll go for the second part. Iron nail near the magnet. When you are keeping iron nail near the magnet, initially it is not magnetized, then it induces magnetization. In other words, it is not equally magnetized. Nail experiences force because the field is non-uniform and induces magnetization. Therefore, it experiences both force and torque. If you are keeping under uniform magnetic field, magnetized needle under uniform magnetic field, there are only torque because equal and opposite forces. But iron nail, initially it is not magnetized, it is induced to magnetize. In other words, non-uniform magnetic field. Therefore, there will be torque as well as force. Okay. Third part. Question is part C question. Must every magnetic configuration have a north pole and south pole? What about the field due to a toroid? I hope it is clear. Each and every magnet behaves like each and every piece has north and south. Now, must every magnetic configuration have a north pole and south pole? What about field due to toroid? First of all, what do you mean by toroid? See, this is the toroid. Solenoid is kept in the form of circle, right? This is toroid. Every magnetic configuration has both north pole as well as south pole because isolated magnetic pole does not exist. But magnetic field lines always forms the closed loop. But in the case of toroidal solenoid, it is an exceptional case, toroid. In a toroid, magnetic field is confined entirely inside the toroid. You can see the blue line here. These are the magnetic field. Outside there is no magnetic field. At the center there is no magnetic field. Magnetic field is confined only inside. Therefore, toroid has no distinct north and south poles, even though it has magnetic configuration. Now we'll go for the last part. A very interesting question here. That is, two identical looking iron bars A and B are given, one of which is definitely known to be a magnet. And how will you distinguish how one ascertain whether or not both magnetized? If only one is magnetized, how does one ascertain which one? In short, two identical bars are given. In that, one is iron rod, another is magnet. We have to distinguish, right? Okay. That is, see, now two rods are given. Time being, both are identical. I will keep one rod like this. I don't know which one is magnet. Let us take a bar A is kept like this. Bar B is kept vertical. I'm moving from this end to this end. Initially, it is attracting. Then, when I'm bringing it to middle, attraction becomes weak. Again, when I'm taking it to end, attraction is more. So, I understood when I'm moving B from one corner to other, one edge to other edge of A, B is not attracted equally. On either side, pulling is more, attraction is more. So, this is A should be a bar magnet. Why? Because across the pole strength is more. That's why B is attracted more on either side. But in the middle, it is a weak attraction. Now, we will reverse the diagram. I'm keeping B horizontally and A vertically. Suppose if B is iron and A is magnet, then it has to attract equally on either side as well as in the middle. Correct? Because now suppose B is an iron rod, A is a magnet, A will be attracted here, A will be attracted in the center, A will be attracted on the edge. On all the points, it is equally attracted. From this, we can conclude that rod A is magnet and rod B is iron bar. Without using anything, we'll be able to distinguish, but we should know the property that in the case of bar magnet, on either poles, strength is more. That's all.